Good afternoon. Let's get started. Our speaker next week will be Helen Curry, who is a senior economist at ConocoPhillips, and she will talk to us on the new paradigm of energy production, opportunities, challenges, and implications for global markets. It's a great pleasure to welcome Greg Nemet, who is an associate professor at the University of Wisconsin-Madison in the La Follette School of Public Affairs and the Nelson Institute Center for Sustainability and Global Environment. He's also chair of the Energy Analysis and Policy Certificate Program. His research and teaching focuses on improving the analysis of the energy system and more generally improving access to energy while reducing impact and footprint on the environment. I follow Greg's work very closely, and I can tell you firsthand that he has made outstanding contributions both on empirical analysis and on modeling of technological change in the broader area of energy, technological change in energy. It's really very inspirational to have followed his work, and it influences my own research in many, many ways. He has been a contributor to the International Panel on Climate Change and the Global Energy Assessment. He received his doctorate in energy and resources from the University of California in Berkeley, and his bachelor's degree is in geography and economics from Dartmouth College. Please join me in welcoming Greg.
Great. Well, thanks a lot for that kind introduction. So I work on technological change in energy systems, and especially the implications for public policy. And my work really goes in two directions. There's a historical branch and a future-oriented branch. And the historical work is really focused on understanding patterns of innovation that have happened in the past. And some of that work includes work I'm doing with Professor Rai right now on photovoltaics and other technologies. And the other work is more normative. What should we do? What are the policy questions? And how can we inform policy questions when we're thinking about technologies to address energy problems, for example, climate change, like the one I'll talk about today. So the project I want to talk about today is really my first attempt in a bigger way to combine those two branches, to take what we know from the historical record of carefully looking at technologies over long periods of time, and use those as inputs into models to think prospectively, what will policy do to technologies and to some of the social impacts that we really care about. So that's what this talk is about today. This is an NSF project that's in the fourth of 4 years. So we're about, the results you'll see are about 75% complete results. The real point I want to talk about, though, today is to think about setting this up as a framework, as a methodology, to really try to get some quantitative insight on this process of innovation that is so probably best characterized as being uncertain and chaotic and serendipitous. And I want to think about ways that we can use quantitative tools, basically simple quantitative tools, to think about some of the trade-offs involved when we think about the uncertain development of technologies. So first, just to acknowledge some collaborators doing work with quite a few people like this: Aaron Baker, UMass, Karen Jenny, Insight Decisions, grad students, and then importantly, and you'll see more of these guys later, 18 experts on carbon capture and sequestration that we spent a lot of time with in this project. And it's really their input which is driving a lot of the results that I'll talk about in a little bit. So some of the premises before we go into some of the kind of approach to this is first that we need technological change to address climate change. So I'm not going to substantiate any of these premises today. I'm just going to put my biases out there so we can proceed from there. That there are multiple market failures at work, so the government has to play some role. So there's pollution externalities, there's knowledge externalities. There may be others as well, but governments have to decide about what they should do. And then with these multiple market failures, there's multiple policy instruments available. We can do carbon pricing in many different ways. We can fund technology development directly in many different ways. That sometimes goes under the rubric of research and development, but includes things like funding education and training scientists and engineers. And then another area of subsidizing early deployment. Maybe there's different market failures at work in early stage technologies when the incentives don't supply the right amount of investment in innovation. So we've got multiple policy instruments available. The government has to decide to do something. And so the broad question this research is trying to inform is, what should governments do? And the angle on it that I think makes it a really hard question is that we're talking about what they should do about technologies that don't exist yet in kind of a full-fledged, full-scale deployment type of the word exists. There are parts of them exist. They work in the laboratory. They work on pilot and demonstration scale, but not in a really big scale. So we're having to make decisions about technologies before we know if they really work, how well they'll work, and what some of the social outcomes might be if we deploy them on a really large scale. So that's kind of the motivation and the policy challenge. I just want to spend like a couple minutes just talking briefly about some of the historical work that's kind of motivated the research design for this future-oriented work. So I mentioned before that the outcomes of innovation are inherently uncertain, but we know something about innovation. There are patterns that we know about, and so I just want to report a few facts that are important for the research design here that have come out of lots of people's work over many years, but what we've tried to capture in this chapter of the Global Energy Assessment that came out last year, and there's going to be a follow-up book that's coming up later this year that goes into a little bit more detail on the many, many case studies of looking at energy technologies and what's led to them getting better or not. So a few things that we know, and let me just point out 4 of them. First is that we're living in a world of skewed distributions of outcomes. So this is ranking different research projects, and the vertical axis is just the payoffs. And you can think that the cost of each of these projects is somewhere here. So when you're doing research, you have to assume that more than half of these projects are going to fail. They're going to not pay off the amount that went into them. And a small amount will pay off in a big way. So this is a general finding for innovation. This is a study of pharmaceuticals, but you can think about it for that these are dot-coms in the late 1990s, and this is Google right here. And so that doesn't, just because we had all these bad, stupid ideas, we call them stupid now, but we didn't know whether this one was a stupid idea or a good idea in 1997 or so. And so that's the challenge here, is you don't know what the outcome is going to be, and that the outcomes are skewed. We're not talking about kind of expected values really determining what's going on here. That's one thing we know. Another thing we know is that economies of scale play a really big role in energy technologies. So to sum up, one of the main reasons why solar is an interesting and important technology now, and it wasn't 30 years ago, is that the scale of production got so big that you could invest in automation, you could invest in robots, you could invest in machines directed exactly for photovoltaics, and then you had fixed costs that you could spread over a giant billion-dollar factory like this largest one in the world in Japan. So economies of scale matter. So when we're thinking about future of technologies, we have to somehow take that into account. Another thing that we know from the past is that technologies get better as you use them, as you gain knowledge just by playing around with them, trying to make electricity, trying to maintain them. A nice example of that is about 350 megawatts of capacity that were installed in the California desert in the mid to late 1980s, and looking at some of the outcomes on that. So if you look at the top picture there, that's the number of failures, and it's basically mirrors breaking because of mechanical problems or storms or other things that had to be repaired. And you can see that rate going down over time. The operation and maintenance costs go down over time as well. So this is different from just building big scale. It's different from doing R&D on making mirrors not break. It's things that are hard to replicate in a laboratory setting in a short amount of time. It takes experiencing these technologies in the real world over sometimes a long period of time, but crucially with lots of iterations to be able to learn about what works and what doesn't work. So learning by doing is important. Another aspect of energy technologies that you can't dismiss are sometimes these things that we often think of as serendipitous events. So the fact that the military developed a jet engine for military use that ended up on these big aircraft to transport troops and equipment all around the world, but that exact same technology with very minor modifications is now deployed in a very important technology, which is combined cycle natural gas power plants, and it's almost the exact same fundamental technology, these gas turbines that are used to make electricity in a lot of cases now. And so that seems kind of random and kind of lucky and serendipitous, but it keeps happening again and again. So that's another thing we want to take into account these spillovers that happen from one technology to another. Sometimes they're technologies that are closely related, and sometimes, in this case, the end use is not closely related at all, even though the core technology didn't have to change very much. So we could go on along, I'd love to go on along these veins, but I just wanted to kind of put out a few of these elements before I kind of think about how we start the research design for this future-oriented project. So let me start working on that. So again, the question is, what should governments do about these uncertain technologies, these multiple policy instruments available? So for now, we're going to say that there are three groups of policy instruments. You can put a price on carbon, you can invest in research in a particular technology, and you can subsidize that technology. So one reason for the subsidy might be that learning by doing that you saw with those concentrating solar mirrors over there. Maybe you want to deploy some of this in an early stage to get up to scale, to get some learning by doing happen, to learn from real experience at full scale in the real world. So there's reasons for doing each of these, but which ones should you do? How much of each one? It's a resource allocation problem. There's another allocation problem, which is we're not just talking about one technology, we're talking about a social problem, whether it's energy security or air pollution or climate change or energy poverty. There's lots of different potential technical solutions, and so we have to think about different technologies we might apply these instruments to. And so in this case, we're going to start by focusing on the middle one here, this carbon capture and sequestration. And we're going to talk about coal plants, just as an example, ways that you could capture carbon dioxide at coal plants and take it away and probably store it underground. And ultimately, what we'd want to do is start to think about allocating across these different policy instruments, across different technologies as well. So in the big scheme, this project is about a portfolio of policy instruments across a portfolio of technologies. And if you had different decision criteria or objective functions, you might think of different ways of designing policy across different technologies. But what I'm going to focus on today is really just thinking about the top three choices with this one set of technologies. And I'll break that down in a minute or two. So how best to choose the level and timing of these three policy instruments to reduce the cost, and it's the cost of CCS. And just to scope it out a little bit, level, so any of these elements here, you could have a lot of R&D or a little bit. You could have really high carbon prices or not. Same with subsidies. And there's timing too. And so we're going to talk about the whole 21st century here. So we're going to be doing modeling ultimately out to 2095. But if you do, depending on how you do the discounting, a lot of that stuff doesn't matter too much. But there's a time choice along this as well. Okay, so that's the general setup of the question we're trying to address here. So here's the question, and I'll keep coming back to this slide here, but our objective here is somehow to reduce the cost of carbon capture and sequestration. So now it doesn't really exist on a large scale. We want to get the abatement costs. So if you think about how much it costs to remove each ton of CO2 that otherwise would have gone into the atmosphere, that's a cost we want to minimize. Or you can think about it in terms of the extra cost of electricity, so the extra price that people would have to pay on their electricity bills if we started building all this stuff and running it and deploying this technology. So that's our objective here, is to reduce the cost of that technology. So in the talk, I'm going to kind of talk about different parts of this schema here, and I'll keep coming back to it. But generally, there's two branches here. The top branch is kind of the early stage work on doing two things. One is making the technology feasible. So can it work over long periods of time with a reasonable amount of maintenance at a high enough capacity factor so that it's under the idea of feasible. And two, there's this issue of energy penalty. Anyone here just so familiar with what an energy penalty might refer to? Just to get a sense. So, okay. So a minority of people, but basically it takes not a trivial amount of energy to run this plant that's going to take CO2 out of the exhaust stream of the flue gas here and take it and put it underground. And it could be something like a third of the energy. So if there are 1,500 big, not giant, but big coal power plants in the US today, if we do this everywhere and we have the same kind of a middle energy penalty that's not improving very much, and we remove all the CO2, we're going to have to build another 500 coal plants with carbon capture to make up for all the power that's going into capturing the CO2. So energy penalty is a crucial parameter that we need to lower. And so the idea here is, can you do R&D for 5 or 10 years that will get these technologies to be feasible and get the energy penalties low enough so that we don't have to build hundreds of more coal power plants. So that's the top branch there. And the bottom branch here is really looking at two things, is how does these technologies get better as they grow? And the two channels we're thinking about there are manufacturing scale, and this is scale not that we're going to build these twice as big, we've already optimized that. It's the scale of the manufacturing facility, so of the components, of the infrastructure to move these around the world and set them up. And so there's a manufacturing scale. So how many of these do you build a year? The more you build, the cheaper they get. And then the second part is that, going back to those mirrors that we're breaking, as you start running them, there's learning by doing, and your operation and maintenance costs go down, and maybe your energy penalty will go down as well. So that's the idea here, and I'll kind of flesh out some of these other channels as well. So we're trying to take some of these things that we know from research on technological change historically, that learning by doing happens, that manufacturing, that scale matters, that research and development matters, and I'll talk about these technology spillovers in a little bit as well. So that's a general approach. I'll come back to this picture a couple times. So the first part I'll talk about, and I'm going to kind of talk about 4 parts of this in the next few minutes. The first part is, in a sense, is the most elusive part of this whole challenge here. And this is going back to whether you should have invested in Google in 1997. If you're investing in R&D, what do you get out of it? And there's dashed lines here because we know that there's some kind of skewed distribution involved. But we don't have a way to say, well, based on what happened with solar 30 years ago, or with internet companies 20 years ago, or whatever it is, this is what should happen with CCS. So what we're doing is using this technique from decision analysis called expert elicitation, where we try to get people that know something about the technology, and we ask them questions within the domain of their expertise about how they think the technology will work out over the next 5 or 10 years under different policy scenarios. So I'll talk a little bit about that in just a minute here. So, and then I'll talk about how we translate those changes in feasibility and energy penalty into costs. Then I'll talk about this learning by doing and manufacturing scale part. And then I'll talk at the very end about what we're going to do next, really, is what we do with the outcomes all of this. So the rest of my talk is really just going through each of these 4 points to kind of give you a sense of how we're putting this all together. So the first part is on this expert elicitation part. So the first thing we've done is made a taxonomy of carbon capture, of ways that you can capture carbon from coal power plants. And so, you could make a more detailed list, and you could make a more aggregated list. And what we wanted to do is find a level of specificity that would give you useful answers, so that it was kind of broken down enough so that each answer meant something and it wasn't going to be changed if you had a slightly different technology. So you wanted a pretty precise list, but you want a short enough list that you can get people to answer questions about multiple technologies. So that was part of the driver for why we picked 7 here. You often see these technologies grouped in maybe 2 or 3 buckets. So these top 4 are considered post-combustion technologies. So you burn the coal, and then you do something with the flue gas, 4 different things in our scheme, to separate out the CO2 and then take it and put it somewhere other than the atmosphere. There's another scheme where you do some of that before the combustion, typically by doing by gasifying the coal. And then these 2 schemes which we're calling alternative combustion, one of which is where you use oxygen and do the combustion that way, and another where you use metals to move oxygen from one side of the reaction to another. So we've got 7 different technologies, and this is going to come up when we talk about technology spillovers, and that's kind of one parameter we're going to have to think about is that if some of these get better, say the energy penalty goes down, does that help the other technologies or not? And so that's something we're wrestling with, and I'll kind of show you the way that we're wrestling with it for now. So that's the set of technologies. So let me talk about this first channel here from R&D to these two parameters here. So the first thing we do, so we've got these 7 capture technologies, and the next thing we do is we're going to think about 3 different policy choices. And so the first one is basically a reference case, a business as usual case. We do about the same amount of R&D that we do now, and we have about the same carbon price that we have now, which is 0 in the US, higher in other places, maybe around the whole world it's in the low single digits per dollar of CO2 if you weight the whole world's emissions. So that's the business as usual case. And then there's 2 alternative scenarios for the future. One is that we have a carbon price and a stringent carbon price. So not a minor one, not the kind that we have in Europe right now, but $100 per ton starting in 2015 and continuing on. And then another one in which we have a low carbon price like we have today, and instead we invest heavily in federal research and development on these technologies. And so business as usual, carbon price with not much R&D, R&D with not much carbon price. And we're going to ask the experts then, what do you think will happen under each of these scenarios? So this was our adventure in 2011, was recruiting people to sit down with us for between 2 and 8 hours, so one person between 2 and 8 hours, with between 2 and 3 of us. So it's a very labor-intensive process. The first 45 minutes of the process is this process or this activity of debiasing them. And the idea is that these people might have biases based on where they've worked. They might have motivational biases based on where they might want their budgets to come from. Lots of different biases. And one finding that comes out of the work in decision analysis is that if you make people aware of their biases, they're less likely to be swayed by them. And so there's some improvement you get if you just talk about biases. So we've spent a lot of time getting them to talk about biases, and we were talking about biases. And then the rest of the interview process, another hour and a half, or another 6.5 hours in one case, is asking them questions, kind of general questions about, what's important with carbon capture, what are some of the challenges that you see, how does your organization deal with these challenges? And a lot of these are kind of rich questions that we take a lot of notes on and learn a lot about, but they're also kind of warm-up questions so that we really get to the heart of the matter, what we're trying to get, which is populating the figure on the top right there, that they're not giving us glib answers, that they've thought through their biases, they've thought through the mechanisms, and then we start asking them things like, what would you say is the most likely outcome for the energy penalty of post-combustion carbon capture with membranes in 2025? So we'll ask them a lot of questions like that, and then we'll start getting at not what their expected outcome is, but what do you think is the 90 percentile in terms of the best you could get, or the worst that you could get in terms of a 90 to 10th range? And so for each of them, we got a range with a median and then a 10th to 90th percentile about their expected energy penalty for each of the 15 experts. And then we look at how it changes, because then we'd start introducing these policy mechanisms and say, if there's a $100 carbon price, what do you think the energy penalty will be? Or if we do a lot in R&D, what do you think the energy penalty will be? So those are the questions, and then we end up with the answers on the top right there, which is for each expert, a range for each of the scenarios with a median and a 10th to 90th percentile range. And the axis there is this energy penalty there. So you can think about that 30% I introduced at the beginning looks like it's kind of a little high for what these guys think it'll be, that roughly 30% of the energy goes to capturing instead of useful electricity. Okay, so that was a year of doing that kind of stuff. So there's more. I'd be happy to talk about them, but I want to talk about what we did with that. So one thing we did is aggregate the results. So we take their ranges, and then we fit probability distributions to the ranges that they gave, and then we aggregate the ranges. And so ultimately for one technology, which this is post-combustion capture with absorption for the business as usual case. That's only what this is. You can see we probably got, I think, maybe 10 or 12 experts to answer that question, lots of different distributions. And so we've aggregated them into this probability distribution. And you can see the cumulative density function on the top there. So you can kind of get a sense of, there's a 50% chance with the aggregated distribution that the energy penalty will be 0.24 or less, something like that. So that's what we're after, and that's kind of the input to our model there. But then when we did that for each technology, for all 7 technologies, and then for these 3 policy scenarios. And so what we're looking at, what we're really after is trying to get this stuff out of the experts' heads. What do they think the effect of policy would be on shifting this probability distribution about energy penalties? And so here's a case with membranes, so ways to separate CO2 from the flue gas using membranes, where here's what it looks like with in the business as usual case, and then as you go to these carbon price and then R&D, you can think about this distribution kind of shifting to the left to lower energy penalties. So we're getting to better outcomes as we get to as we get from business as usual to carbon price to R&D. Oh, and the reason why each of them don't end up at 100% is that we've got the feasibility in there too, so they can only get up to the level of feasibility. So that's part of what makes them differentiated as well. Okay, so this is really the input data for the part that I'll talk about next. So expert elicitation, we're trying to make this connection between R&D and some of these outcomes. And then just one comment before I move on here is that it was surprising to me how pessimistic the experts are that R&D is going to get to much better energy penalty. I really thought that they'd have a strong motivational bias to say that if you just give us the R&D, we'll do this big research effort, we'll be well funded, and we'll get you the energy penalty you want. And it really does not seem to be the case. So we're actually going to do some more work on expert elicitation in general for lots of technologies to see if there is almost this, the direction of bias actually I think goes in the opposite direction that most people think. Okay, so I now want to say, okay, so we've talked about R&D, get to energy penalty and feasibility. The next step is to take, say, a 30% energy penalty, and what does that do in terms of the cost of carbon capture? So that's this next set of lines up here. And let me just give you a little bit of the results from that. But the basic idea was to do this kind of middle-level precision model. So not a fully specified, detailed bottom-up model, which a lot of people working on CCS would use. So something more aggregated than that. And not a top-down treatment of CCS like almost every integrated assessment model that's used to do the costs and benefits of climate change would do. So something in the middle where we can use the expert elicitations, but at the same time precise enough so that we can actually think about how the parameters would affect the cost. So these are kind of different components of cost. And then we've got different assumptions that go into affecting those costs, two of which are coming from the expert elicitation, energy penalty and feasibility, but others that we get from the literature, like capital cost, how much it's going to cost to move the CO2 around, and then operation and maintenance costs. So we use a wide range of assumptions on each of these, and ultimately, and I guess I'll just get to this in a couple of minutes, we have distributions on each of these things from the expert elicitations, but we also have distributions from the literature, so we can propagate each of these distributions kind of through this kind of middle-level bottom-up cost model to think about what the effects are on costs under different assumptions about these parameters and under different policy scenarios that would affect the two channels on the bottom there. So this is just some benchmarking. I'm not going to spend time on that. So we did some sensitivity analysis to figure out what aspects of this cost model matter the most, and we came up with 7 here. So capital cost, what discount rate you use, how often the plant is running, that's the capacity factor. And so going back to that figure before, so we've got distributions for each of these 7 items, and then we push those through the model and see what we get out on the other side. So here's just the sensitivity analysis. But But here's where we start propagating it through, and so we get distributions of costs. So on the bottom there, dollars per ton of CO2. And these are the 7 technologies that we're looking at there. And you can see the idea with this policy is that scenario 3, the R&D, shifts things to the left, makes the cost cheaper. But the other thing I think you'll see is it doesn't shift it very much. So all this variation that comes from what you assume about capacity factors and discount rates and especially capital cost really dominates and creates this range of uncertainty. Whether you invest in R&D or not gives you an incremental change relative to the uncertainty in those other parameters. So that's just one kind of takeaway, and I think that's just a picture of it here. Let me just talk about this one for a little more carefully. So this is where we have the 7 technologies, and they're competing with each other. So we push these parameters through the model. There's 7 technologies, and I think there's 100,000 iterations here. But in each iteration, one of these 7 technologies wins. It wins because it's the cheapest way to capture CO2 from power plants. And what comes out here is that it's not perfectly distributed across the technologies. And the distribution of the whole CCS capture program, you might say, is the top there. That's kind of the distribution. We could have outcomes as bad as above $100 per ton and as good as under $30 per ton. But it's which of these technologies are contributing to that outcome. And I think the numbers there on the side are for these 100,000 iterations, how many times does chemical looping come up as the best technology? So 17% of the time, or in 17,000 iterations, chemical looping is the one that wins. It's also the one that gives you the lowest cost carbon capture. And that might be something to consider if you're thinking about not just carbon capture, but nuclear power and solar power and other ways to produce electricity with lower amounts of carbon emissions. So this is really competing technologies here. And one of the outcomes here is that there is a real benefit to diversifying the technology strategy. So if you look at this and you say, well, the best technology, the one that gives you the cheapest cost is chemical looping, so we should focus on that one. And most of the time, chemical looping is not even going to work at all, so then you're left with nothing. If you focus on the one that wins most of the time, that's this pre-combustion capture, that's only 30% of the time. So there's really a benefit to diversifying the R&D strategy. We haven't talked about what the cost of diversifying it, so it may not still be a good idea to do it, but there really are benefits that come from diversifying. The costs are another question. So, okay, so that's looking at how the cost outcomes are, and what's driving this distribution is things like discount rates, capital costs, capacity factors, but also energy penalty and feasibility, and that R&D versus carbon prices might make an effect on that. Okay, and this is to kind of isolate the policy effect a little bit. If we pick a target, so say we want carbon capture that's $60 per ton of CO2 or less. First of all, what are the chances of getting to that if you get all these technologies in the game? And you got a 28% chance if you do business as usual, like today, and you get up to 34% if you do an R&D program. And so you can make your own judgment about whether that's a big difference or a little difference, and it probably depends on how much you're going to actually spend in R&D, how difficult or expensive would that be. But that's the type of comparison we're starting to try to do here. Taking this full uncertainty into account, what should you expect from an R&D policy? And you could do something similar from carbon prices without much R&D. What would you expect from that? And I think I remember the answers in between the 28 and the 34. Okay, so that's that top channel there. I want to spend a little time now, and then wrap up with what we'll do next, on this bottom channel here, because that's the part that's really in development now. So let me work through that one with a couple of slides. So the main idea here is we talked about these historical mechanisms for technologies improving, and that we're going to characterize. What really drives economies of scale, learning by doing, and those improvements is building more or building bigger, and that is a function of how much demand there is for CCS. And so that's a crucial input here if we're going to work on this bottom channel of learning by doing and returns to scale. How much CCS is there actually? And part of the reason here, if we want to get technological change, there's other reasons to do carbon pricing, but if you're interested in technological change from carbon pricing, part of what carbon pricing gets you is a demand for technology that there's really almost no reason to build a carbon capture sequestration plant without a price for carbon. I mean, maybe there's a price for carbon because people are making food processing or trying to get extra oil out of the ground, but that's probably small compared to what it might be if we did a serious carbon price like what we were talking about before. And then also if you had an early subsidy, sort of like we have for nuclear power, for wind power, for solar power, actually any energy technology today has some subsidy in the early stages especially to drive it into the market, and part of that is because you get scale and learning by doing. So these are our policy choices there, and here's this bottom channel. So let me just kind of describe how we're doing some of that. So one of the most complicated parts of carbon capture and sequestration is where the demand comes from. And so in our model here, demand is a function of how much the technology costs, how much subsidy you get, how much there is for carbon price, if there's some kind of spillover, and I'll talk about that in a little bit, and then over time, generally demand increases for the whole world as energy consumption increases as well. So what we're doing here is using an integrated assessment model, but going backwards with it and trying to figure out how much, and this integrated assessment model is taking all kinds of energy technologies and they're competing with each other. And as we vary carbon prices, subsidies, prices for CCS, what do we get out of it? And so by running that model many times, we can kind of impute a demand curve for CCS. So here's one example of what it might look like. And I got the axes are a little bit opposite from what a normal demand curve would look like, but the shape is similar. So as you get to lower carbon prices, you get higher demand there. So that's kind of a basic demand curve for CCS at $100 per ton. Here's where it starts to look complicated is if you say, well, it's not just $100 a ton. Let's think about the choices we have for carbon prices. You could have 15, 30, so going from $15 to $200 a ton, and then how that changes over the century. So this model is goes out to 2095. So one thing that's kind of curious here, and this is part of what makes CCS more complicated than other technologies, is you don't optimize demand for CCS by having a really high carbon price. That's true for other technologies. But with CCS, because you're not capturing all of it, there's some leakage, maybe 10% of the CO2 still goes in the atmosphere. If you start charging a lot for that 10%, people are going to start using less CCS. Or they might just use zero carbon energy technologies if the price is really high. So we've got this funny thing where there's not necessarily, a low carbon price isn't enough to get CCS built, and a high carbon price gets other stuff built, at least in the longer term. So we've got these funny demand curves. I can talk about that maybe more in the questions if you're interested. But that's something we've been wrestling with here. If we're thinking about trying to reduce the cost of CCS, it's not clear which carbon price is actually going to get you the best outcome. So there's demand. Here's just kind of an example of how we're doing this next stage is when you get demand, how do you get a cost? Here's the cost structure that comes out of that work I talked about before. So here are the 7 technologies here. And so part of that cost comes from the energy penalty. That's the darkest part on the bottom, the operation and maintenance cost, the capital cost. And then how do those change over time? So here we're going back to the historical record. We're looking at things like sulfur dioxide removal, so flue gas desulfurization, NOx removal from power plants, so selective catalytic reduction. You can look at how those technologies have improved as they've been used more, as we've captured more SO2 or captured more NOx. And so those give you learning rates, and you can make those into an exponent that's useful for a calculation here. And so we're using this historical data to say that energy use declines similar to these other analogous technologies. Process costs go down like that. Transmission and storage, we're saying at least there's uncertainty about what it will be, but there's no direction to the change. So it could get lower because there's economies of scale or learning by doing and moving the stuff around and developing a network. And there could be rising costs as reservoirs get depleted and you have to start moving stuff further across the country to get to reservoir space. So we're assuming that's not changing it now, it's fixed. And then capital costs, it's not learning by doing there, it's this manufacturing scale. And you'll see in a minute that manufacturing scale is not monotonically increasing. Because of these weird demand curves that go down over time, there's kind of this golden period for the CCS industry between about 2020 and 2040 when everything's growing and building. And after that, these plants are made, they're going to last for 40 or 50 years. There isn't a lot of demand for building more of them. So there's a big pulse of them early on that fades later. And I think I'm going to show that to you next. So, and then so basically how we're doing something like capital cost, it's a function of what the capital cost was in the year before, and then how much the manufacturing capacity is increasing, and then that B value is this one here. So that B value can change, and we'll talk a bit about that, but that's the idea for how capital costs might change over time as you get bigger manufacturing plants. So what all this produces is this kind of this endogenous system where you're having demand for CCS, you're having plants get built, that reduces costs, and then as costs go down, you get more demand for CCS in the next period. So we've done it in a sequence so that it's not just a kind of a closed system here. We're kind of stepping it over time. But here's what makes this one complicated or interesting depending on your perspective. Here's this is the real demand for CCS over time. So at this carbon price, and I don't think I specified what it is, you get this peak in demand around 2050, which is pretty true about almost any carbon price. In terms of building new plants, you're building, manufacturing scale is increasing until about 2040, and then you're still building new plants, but the manufacturing scale goes down. And then after 2050, when demand starts going down, but you've got this big stock of 500 or 600 installed CCS plants, you start mothballing plants. So they're there, they could work if you want to, but it's not worth running them, and so you turn them off. And then there's a little pulse towards the end as you get some of these initial stock retiring and you have to build new ones again. So there's this demand, this build out, and as you build them, the costs change and come down over time. So that's a lot of what we're trying to simulate across lots of different carbon prices, different other policies, and different assumptions too, and I'll talk about that in just a couple of minutes there too. Yep. So what we're going to do now is, so I showed you that kind of rainbow figure before with all the technologies because we had distributions of capital costs, of energy penalties from the experts, feasibility from the experts for 2025. We've got additional parameters in the model if we're going past the R&D phase and trying to simulate manufacturing scale and learning by doing. So there's the parameters here that vary and do vary, and we've got historical data on what those distributions look like. We've got spillovers across technologies. So if you have learning by doing in one technology, does that help the other technology? And so we can have different assumptions about that. And then there's this other parameter here, which is are there differences in those 7 technologies so that it's not actually a winner-take-all race? Whatever one's cheapest gets all the demand, but are there characteristics about what type of coal you're using, where the location is, that would give you some market even if you're not the cheapest capture technology? And so we're kind of varying how big these niche markets are, and that determines whether the cheapest technology gets 100% of the market or 50% of the market or something in between. So we start doing the same exercise as before of kind of pushing distributions on each of these through the model, including the uncertainties above on 2025 through the model. And so here's kind of the full uncertainty about what deployment looks like in, I think this is all carbon prices, all subsidies, different levels of R&D, and then all those parameters before. So you've got some central value in the lightest part here. You've got a large span from almost no build at all for the next 30 years to almost 1,000 plants being built. But a lot of these, that range is driven by these really long tails here. So you can think about this distribution going vertically. And this is the lower tail, and above the dashed lines, the upper tail. And the 10th to 90th percentile there is what these black dashed lines describe. And so based on whether you have lots of learning by doing or a little learning by doing, lots of spillover from one technology to another or not, niche markets that preserve other technologies or not, you end up with this distribution in terms of how many plants get built. It's a distribution that affects how much each technology costs. And here's what all of them together look like. And yeah, I guess this is the last one I'll show on here, is kind of, this is getting towards more of a social objective, how much CO2 gets avoided, gets put into the ground instead of up into the atmosphere over the whole century from CCS. And you know, if you restrict yourself from the 10th to the 90th percentile here, it's not a gigantic amount of uncertainty. And that's almost been a surprising finding for me, is considering how much uncertainty we're taking into account on each parameter, and then how many parameters are actually varying, which is probably 12 or 15 altogether, simultaneously, that you end up with a range that is not that big. And I think a lot of that is driven by what these demand curves are for CCS. And the demand for CCS is not that sensitive to how much CCS costs. There's a lot of demand for CCS if we start getting into stringent climate change targets. But if CCS gets really cheap, that doesn't necessarily lead to a gigantic amount of CCS. That's really different from another technology that we've done this whole same treatment to, which is photovoltaics. Whereas as they get cheaper, the demand really takes off. And there's much less demand at costs that are kind of comparable to other technologies. So it's a really different type of output, and it really comes from these demand curves having this really an up and down shape to them. Okay, so I just spent the last 2 minutes here talking about what we're going to do next, because we haven't done it. And you know, I haven't given you the punchline to this whole project too, is which policies work best, which policies are robust to these many different worlds that could come out. And that's kind of what we're working on now. So we're taking these distributions of the cost of CCS, of this, how much CO2 gets captured, and starting to think about if we start varying carbon prices, subsidies, and R&D, what's kind of an optimal allocation that gets you maybe the highest expected value in terms of CO2 captured, or lowest expected value in terms of the cost of CCS. Or do we do it in the second bullet point here, which is, are there policy combinations that would be kind of have the least regrets to them, for example? Maybe if we have a target of we want CCS to be $50 a ton or less, what policy combinations are most likely to give us that under all these different scenarios? Then starting to put some of these outcomes in an integrated assessment model that can include technological change. And that really allows us to think about what the benefits are of having cheaper CCS available. And so far all I've talked about are these policies that might give us cheaper CCS, but the policies cost something. You have to invest hundreds of millions of dollars in R&D. You have to pay for a carbon tax. You have to pay for these subsidies. But what are the benefits of that in terms of social benefits? So avoided climate damages or avoided mitigation costs. And so that's something that we're doing simultaneously. And then going beyond CCS, as I referred to at the beginning, what happens to the policy mix if you start including combinations of technologies? And so what we're going to do, at least to start with, is to put the same treatment for solar together with the same treatment for CCS. How do you get kind of net benefits from climate change abatement under these different policy scenarios? So, okay, I'll leave it at that. I apologize for skipping over, these are long talks for each of these 4 chunks, but I just want to give you really kind of the framework of what we're doing, and happy to take questions as well. So, thanks. And as you can see, this research is really still in process, so the questions are very helpful. Oh, no, you pick up. Maybe we'll start in the back. Just.
Who has their hand up? So my question is, other than in business as usual, how much it depends on what other countries do as well?
Yeah, so that's a good question. So, yeah, I'll write that down because we haven't done that explicitly. We did tell the experts that other countries may put a carbon price in the R&D case, but it's up to them to make their own assumption on that. So what you're getting at, though, is a real kind of degrees of freedom issue we have. I mean, we asked these 3 very simple policy scenarios. You can imagine multiplying those by 2 by saying China does a lot, China does little, and it already took an average of 4 hours with each expert. So that's something that we're going to have to figure out. And one of the options here is, I talked about all the benefits of sitting in a room with them and debiasing them. At the same time, we've done another study where we do this online and have them answer questions online. And now what we're going to do is put all those together and see if there really is a bias or some help. Because if it's not worth spending all that time with them, maybe we can ask more specific questions like that if we do a more less labor-intensive medium like an internet survey. So, thanks.
So I was wondering, in general, you noted the various sensitivities in your model to both the kind of expert component versus the kind of stochastic parameters based on the price elasticities, things like that. I wonder if you could address that a little further and then also go back to the slide where you showed the distributions of the expert opinions. Mm-hmm. It looked like those were really, there was a lot of heterogeneity in those distributions. I wonder if you could just talk a little bit more about that.
Yeah, so the first one, which parameters matter? So this bottom picture, which I kind of skimmed over, this is just a one at a time sensitivity, but it does seem to hold if you do them simultaneously. What the capital cost is makes a really big difference, and the discount rate you use makes a really big difference. Those are the big 2, other than energy penalty, that matter. And they're very different. So capital cost, it's hard to know exactly what that is. Is it labor costs that might change over time or over space in different countries? Is it that we tend to underestimate the complexity of early stage projects and they tend to be more than we thought? Or is it steel and concrete and input materials prices and things like that? So if there was a value of information study to be done, it would be really honing in on why is there such a big distribution in capital costs. And I think we know why that affects the ultimate cost, but why is the kind of the input assumption so unknown? And I think maybe the short answer is if you built 10 big demonstration plants, you would probably reduce a lot of that uncertainty there. And then the second question was, why are the expert opinions so different? Is this the one with the people's faces on it? Is that the one?
Yeah, that one right there.
This one?
Yeah. I'm just looking at the...
This is the individuals.
Yes.
Okay.
And then you're aggregating at the...
Yeah. So I think part of the answer to your question is, there are choices to be made in how you take 3 points, a 90th percentile, 10th percentile, and a 50th, and turn that into a distribution. I think that probably affects why these things look so spiky, is that we don't have that many points for each expert. But also that they are quite different, and you see that here. And I guess one takeaway just from the top right there is, I think this is the way to say it, is there's a lot more variation from one expert to another than there is from one scenario to another. And that is ultimately leads to this aggregation process here. So this takes the 15 experts and puts them together. And the assumptions that go into making one distribution out of 15. But I think that captures some of that idea. But you can see in a lot of cases, maybe because we did a good job of debiasing them and trying not to make them overconfident. I mean, that's something that comes out of these past studies too, is that people tend to underestimate how much uncertainty there is. And you're a few of these people that seem a little too confident, given what the aggregate universe says. But in general, there's a lot of different worlds they can imagine of things being a lot worse or a lot better. But not big shifts in the median or even their 10th and 90th from policy. So, Should probably take another question. Yep.
Oh, coming down.
Very interesting study. My question is, so for those parameters getting into the, I guess, demand pool technology change track, so those parameters are drawn from the historical records, right? Not from experts.
Yeah, like the learning by doing rate and things like
Yes,
that?
and the capital discount, capacity factor capital.
Yeah, right.
And how, what's the, how valid that for that parameter, the distribution of that parameter from the past can be approximate for the next 100 years.
Yeah, okay. So I'll say the learning by doing and the returns to scale is something that we really took from the past experience. But these other parameters here are really coming from, and these are just references, numbers in a paper, that are other studies of CCS that say that they expect a capacity factor between 0.65 and 0.85 with a mid-range value as the expected value. They could be wrong. They could be overconfident. They could be maybe underconfident. Maybe we know those more precisely. But yeah, that's where we took the literature. We asked the experts questions along these lines, but not in a structured way that we could use their responses as elicitations. We asked them questions like, would R&D influence capital cost? And because that's important. And they said no, it wouldn't. And that seems to be a pretty robust response from probably 2/3 of the experts that had an opinion on that. So it's still, what is driving capital costs? Or maybe the other way to say it is it just stochastic, or is there a way you could reduce capital costs and get it to the lower range rather than the higher range? And it probably is demonstration plants or something like that, at least to reduce the uncertainty. Whether that actually reduces the level, I don't know, maybe there's something else for that. But that's kind of another study to do, I would say.
And sorry, one more, just very quick. So what's the decision rule for building a new plant or not?
Oh, for doing a new plant or not?
Yes.
Yeah, so that's in this minicam model. And so your cost of electricity, so your levelized cost of electricity has to be, taking into account carbon prices and subsidies and everything, has to be lower than other technologies that could compete in that same market. And there's constraints on how much solar they can be, constraints on how quickly they can change, constraints on how much CCS they can be. But I think that's generally the issue there. And what that raises, though, is that you've got levelized costs of a new plant competing with marginal costs of an existing plant. That's partly what makes replacement difficult. It's hard to retire existing plants because they last a long time and their operating costs are pretty low compared to the full costs, including the capital costs of a new one. So, yep.
I just wanted to ask a question about the local favorite. Are you familiar with the company Skyonics, which is doing a carbon capture demonstration plant near San Antonio? So I was curious about that.
Yeah.
But if the answer is no, that's a short answer.
Yep. I mean, I think that's actually one of the encouraging parts about doing this work is that there are these, it's not just large power companies that are doing this. It's not just government labs that are doing this, that there is some examples of companies, for whatever reason, doing their own carbon capture. And it might be that they expect a carbon price in the future. It might be that they see a large niche market in enhanced oil recovery or something like that, or using CO2 for other byproducts where it might be useful in the chemical industry or something like that. So, but yeah, it's good to raise that. I think the other thing, though, is that I guess your question makes me optimistic. The reactions of the experts, though, makes me really a little pessimistic. It was surprising how not surprising. The experts are pretty discouraged about, they've been working on this for 20 years. That's why we found them. That's why we picked them, because they have a long publication record. And, and we still haven't built a full-scale operational CCS plant after all this time. And so a lot of them were saying, we don't want more R&D. We've done enough R&D. We need more deployment of the technology. Then we'll do the R&D, because then we'll know what to do the R&D on. We'll have new problems that will emerge when we build a real plant, and then we start doing R&D. So I think that's something that comes out of it. The other thing that I was a little interested, just kind of qualitatively talking to the experts, is, one of them said, are you surprised that after all this time we haven't converged on a preferred solution yet? So in our taxonomy, there's 7 different carbon capture technologies, and in our modeling, almost all of them have a pretty good chance of working and of making a real contribution. And when you go talk to people, we found people working on all these technologies. And so it's interesting that there isn't a convergence on, like you see in solar, where it's crystalline silicon solar, and that's more than 90% of the market. And you see it in other technologies too, where you have this convergence on a dominant design, there's benefits of scale, you start improving it, and it takes off. And with CCS, everything's kind of still open yet. And it's probably because we haven't actually built anything yet, and so you don't have those kind of positive reinforcing effects. Great. Thanks a lot for all your questions, comments. Thank you. Thanks, Bruce. Great. Thanks.